Hi everyone, welcome to the first video in the Math 104 Introductory Calculus video series. We're kicking it off today with volumes using cross sections, which I found to be one of the coolest applications of definite integrals that at least I've seen as a calculus student. The basic idea is that we have this volume floating around in three-dimensional space, as volumes do, and it can be as crazy as we want it to be, right? We can make it look like this. And our goal is to, try to find the volume of this object here. And at first you might be like, there's absolutely no way this is possible, right? Because look how crazy that is. Well, the idea here is that, we're not going to be using a formula like 4/3 pi r cubed. We're going to use a little trick called, of course, cross sections. What we're going to do is we're going to zoom in really, really far. We're going to take a knife and we're going to slice our volume. In this case, vertically, there's nothing stopping us from doing it horizontally like this. But let's just look at the vertical case now. And we're going to zoom really, really far in and take it out. And we're going to extend it just a little bit. So we're going to have some area here that the essentially base of this cross section takes up. And then, we've seen this before, but we make it a little bit wide. We give it some width element to it. We'll call it dx for now. And the idea here is that if I'm able to go at every single point x in this interval, we'll call it from A to B, and I'm able to draw this cross-sectional area, and I'm able to, get the area of it, then what I can do is I can integrate the area of each piece times dx over my bounds here, and that will give me the total volume I'm after. Okay, so we've seen stuff like this before. We've dissected objects into really, really small pieces and added them all up using an integral. And so this isn't really anything we haven't seen before. The tricky part of these problems comes from, first of all, finding the bounds of your integral you'll need to be doing. And the second part is the most difficult part, of course, is finding the area. And in this particular case, well, I guess in general, you have to keep it as generic as possible. So you want your formula for your area to work at every particular x within A and B. Okay, so I think the best way to illustrate this is just to jump in and do an example. This might be a problem you'll see on a final or something. It's pretty similar, right? So we have a bunch of information in front of us. We have a solid that lies between those two x values. They said our cross-section is perpendicular. Remember, it could be either, but we'll deal with perpendicular to the x-axis. And then we have squares that are diagonal from y is equal to that to y is equal to, the positive of that. The easiest way to do this is honestly just to draw a picture. So let's take a look at what this looks like in the plane. We have y and x here. I have my bounds. Nothing's outside of -1 and 1, which is convenient. And then let's draw where our squares are going to and from. We simply recognize this as the unit circle, right? So I have the positive unit circle part up here and the negative unit circle part down here. And then I didn't word this very well, but my squares have diagonals that lie spanning that distance here, right? So it's not looking like this, where I have a square popping up. It's instead looking like diamonds kind of coming out of the page and then going into the page down here. And that's the cross sections we're dealing with. So again, what we're trying to do here is we're trying to find the area of a generic square at any point between -1 and 1. And then we're going to integrate that over my entire bound. Okay, so let's go ahead and do that. Let's pull the geometry out here. I find that's the next easiest thing to do so your diagram doesn't get too messy. This is what we're working with. We have this diagonal here we know to be the distance from this point to the x-axis, and then again from the x-axis to that point up here. But the distances are equivalent, right? So we can just make it 2 times that distance, like that. And then we know that we're working with squares, right? So this side of the square is equal to that side of the square. We know that the area of my square is just going to be s squared. So the name of the game here is to find s. We're equipped to do that, right? We know trigonometry. So let's go ahead and break this down even further into this type of triangle here, where we have just the square root of 1 minus x squared. I have s up here. And you know what, let's not even do that. Sorry. This is a 90-degree angle, right? So let's just use Pythagorean theorem here to do this. We have s squared plus s squared, right? The two legs of my triangle. A squared and b squared is equal to c squared, which is 4 1 minus x squared. So I essentially get s squared is equal to 2 1 minus x squared. And in general, what you do is, you'd solve for s, which is square root of 2, square root of 1 minus x squared. But if you notice, our formula is already a is equal to s squared, so we can go ahead and just pop that in there. Okay, so what we're doing here then is we found the area as general as we possibly can at any given point in my interval. So if I want to draw my square here, for instance, I can find the area of that square simply by plugging in the x value to this equation here. And this makes sense to us, right? So the biggest square we can possibly draw would be when the diagonal is biggest, right at the origin. And then the smallest one would be when right at the bounds, when x is equal to 1 and x is equal to -1, which not coincidentally gives us 0 as an area. So what we're doing then to find the volume of this whole thing, you're going to be integrating my area formula from a to b. We're going from -1 to 1 in the x direction. We're integrating 2 1 minus x squared dx. If you work that out, you should get 8/3, I hope. But yeah, this is essentially, a typical problem using cross sections here. So what this will end up looking like if you were to draw all of these out is you have these diagonal lines essentially, pretty sharp, making up the edges, but it's getting smaller, so it's almost like a football looking shape as you continue to draw these cross sections. Okay, so let's go ahead and do another example. This one's a little trickier, but nothing we haven't seen before. So we have another surface that lies between x is equal to 0 and x is equal to pi. We have perpendicular cross sections to the x-axis, so same thing we did before. This time the cross sections are equilateral triangles with bases running from the x-axis to a function to square root of sine x. So again, let's go ahead and draw this picture. We have x here, y here. The x-axis is the same as y is equal to 0. And then we have this function looking like this, which is y is equal to 2 square root of sine x. And then our bounds here run from x is equal to 0 and x is equal to pi. Okay, great. So, you'll be looking at this on the exam and be freaking out because it has a square root of sine x, but you don't know how to integrate that, so we're going to hope that it goes away, and indeed it will. So the next big important piece of information for us is the geometry of our cross sections. So let's go ahead and look. They're equilateral triangles, and our bases are running perpendicular to the x-axis from y is equal to 0 to y is equal to that function. So it looks something like that popping out of the page at us. So let's go ahead and, again, extract that geometry here. We know the base, for instance, is 2 square root of sine x because it's this distance here that we're looking at, right? But since it's equilateral, we also know that this side length has to be that as well. And this isn't so important, but so does this one. The area of our triangle that we have is, of course, base times height. And so what we need to do then is we need to reduce this triangle further. So we end up with something that we're familiar with from trigonometry. So let's divide that base in half. Let's look at just this part over here. I have the square root of sine x because I cut that in half. And then notice that if we cut an equilateral triangle in half, we're left with a 30, 60, 90 triangle that we're familiar with, which tells us that this over here needs to be square root of 3 times the square root of sine x. So we know our base is this, right? It's not this. This is just the one we used in our trig function. So it's 2 square root of sine x, and our height we just found through trigonometry to be root 3 root sine x. So our area at any given x value is going to be 2 root 3 times sine of x, which is not terrible, right? So we'll be integrating this to find the full volume between 0 and pi. 2 root 3 times sine of x. We know the integral from 0 to pi of sine of x is 2, so this should give us 4 root 3. Again, I hope. But anyway, notice how little work this actually took on paper. A lot of it is just being smart about how to do the trigonometry sometimes, and sometimes you're left with complicated functions, bounds, or honestly, the cross sections themselves could be parabolas or something pretty crazy. But as long as you're comfortable with the process of identifying the bounds, identifying the geometry of your cross section, I think you should be good to go.